So there we go. We're live here. Let's go back to our own the earlier discussion with minimum and maximum problems. And today we're gonna do a few more of those just to exemplify even further the concept that was learned last time. And I expect everybody, again, since we do problems, and many times we do problems here, a lot of problems. So I expect everybody, I saw there's activity on YouTube, on the channel, and also, this lesson will be on YouTube. So I expect everybody to really go through these lessons carefully. And when they get to a problem, so kind of stop the video, watch the statement of a problem, try it yourself, and then do the problem. Then watch the problem solved by me here. So I'm going to do yet another example. So this is going to be number 31 from section 3.1. And I got my book here. I'll copy the problem from the book. It says that f of x equals, and the formula is 2x cubed minus 3x squared minus 36x. All right. So what kind of function is this? This is a cubic function, and if you really want to see, folks, if you really want to see what this looks like, let's take a quick look at decimals, and let's see how that looks like before we do anything on this problem. So I'm going to share with you. Folks, now. I'm going to share decimals here. There we go. That's decimals. So let me just make sure that you actually all see that. So you all see that? Yes, you do. And over here, I'm going to typeset the exact same thing. So f of x, f of x equals, and I'm going to say here 2x cubed minus 3x squared, okay, plus, and for whatever reason, why does it typeset with capital letters? I think I have a tab. Oh, caps. Okay, had the caps on. Sorry about that, folks. Oops. X squared here. There we go. My apologies. Keep the caps down here. X cubed minus 3x squared plus, and I'll say minus the 36x. All right, minus 36x. All right, so this is the function, and this, has like a strange graph, well, and maybe not so strange. So you can see it goes up, and oops, you have to zoom out a lot to see the shape of a graph. Essentially, folks, essentially goes all the way up and it comes down and goes all the way up. So you can actually tell easily that this point here, this here, will be -2 and 44, will be a point of local maximum. And this one point here at the bottom will be 3, comma, -81, will be a point of local minimum. So these will be critical numbers. The derivative of our function f will be 0 at those numbers. This is what the problem wants us to find. Now, as you can see, none of them is an absolute something, absolute minimum or absolute maximum. So for instance, 3, -81 is a point of local minimum. But of course, if you go a little to the left over here, you will see this one point, -4, comma, 82, for instance, comma, -120 point something. So that's much lower, this one over here. So there are points lower, and obviously there are points higher on the graph. So this graph here is not something that has absolute anything. So it doesn't have absolute maximum or absolute minimum. It could go as far as you want up high and as far as you want down low. So, but it has some points of local behavior like this one is. So, so locally, this one is the highest, and this one is the lowest in a small neighborhood here. So, that's what we are going to do. We are going to calculate the derivative and see that those are critical numbers. So the critical numbers, as I told you folks, are the numbers where the derivative is equal to 0. And that's what you have to do, to set the derivative equal to 0. And it's nothing easier than this. Just saying that the derivative is 6x squared minus over here 6x minus 36 is equal to 0. And when you have that equal to 0, you can factor 6, and that 6 times x squared minus x minus 6 is equal to 0. And you can factor here further, so you can say 6 times x minus 3 times x plus 2 is equal to 0. Now, everybody is required to remember how to factor this kind of trinomial. So, so if you forgot that in pre-calculus or so, when you learn that, do review that, because that's important, or college algebra or so, high school maybe. So folks, all right, let me make sure that we all see the same thing. Yep, we do. So folks, how do you figure out this splitting? If simply look at -6 over here, -3 times 2 should be -6. So that's going to give you a hint of what these numbers here should be, -3 and 2. All right, so with that being said, the solutions are x equals 3 and x equals -2. So these are the critical numbers. And if you remember in Desmos, we figured that those numbers are the ones that you can put up there, and you can find the corresponding points on the graph being local maximum and local minimum. All right, but the problem is only asking for these 2 points, and they perfectly make sense as I explained on the graph. So we're done. This is the answer. These 2 numbers here. All right, so folks, it's as simple as, calculating critical numbers is never a difficult problem. It's as simple as setting the equation equal to 0 and figuring these things out. All right, and there's other problems here that are a little more complex. There's problems with fractions, problems with some problems with trigonometry. I'm going to do one of those here. But in practice, folks, you will rarely do those things. So I'm going to do one of trigonometry just to have something, some sort of variety here, because you might tend to think that this critical number discussion is only for, polynomials, for powers of x. No, it could be for trigonometric functions. And the example that I'm going to do here is number 41. This is a bit of a trickier problem. It requires a little more trigonometry than we used to use in this class. So this is the problem from, so section 3.1. All right, and this problem says, so it says f of theta equals 2 cosine theta. I'm going to write it this way, or I don't like to use the Greek letter theta, but well, anyway, let's use it, plus sine squared theta. All right, so let me sorry about that, folks. So let's write, they don't write with parentheses in the book. I'm going to write it like them, sine squared theta. This is our function, and the problem is to find points of, find the critical number, find its critical numbers. So f prime of theta equals 2 cosine theta prime, that's going to be -2 sine theta. So as you remember, the derivative of cosine is -2 sine. It's a good review here. Plus And the next thing, sine squared, is, remember, the sine of theta all squared. So it's the derivative of a square of a function, which is 2 sine theta to the first, right, times. And then the derivative of sine, which is cosine. So over here, we did the chain rule to calculate this derivative. This is what we want to set equal to 0. And to set this equal to 0, again, you will have no chances if you can't factor, but you could luckily factor here. So let's factor negative 2 sine theta. And then we're going to get 1 minus cosine theta here. And that should be equal to 0. So the answer to this problem is, so f prime is 0 when one of these two is 0, right? So either sine theta is 0, or 1 minus cosine theta is 0. And these have two different solutions. So sine theta equals 0 means that theta equals 0, pi, 2 pi, and so on. So the multiples of pi, folks. Of course, it could be negative numbers too. So we could put plus, minus, etc. So that would be one type of solution. And over here for 1 minus cosine theta, cosine theta is equal to 1 when theta is equal to 0 or 2 pi or 4 pi, because it's got to go around the circle every time it hits 0 for cosine to be 1. So remember, this is kind of where we review the values of sine and cosine. Again, the level of trigonometry that we use here is that the level of knowing the values of sine and cosine. But those are something that you really need to know. So we get these numbers, the even multiples of pi. So solutions are, we can say, since these solutions are always included in this bigger set on the left, solutions are theta equals 0. We can put pi, 2 pi, 3 pi, and also negative pi. Forgot to put that. Yeah, I'm not going to put plus or minus. So I'm just going to say here, negative pi, negative 2 pi, negative 3 pi, So over here, we got all the solutions for this problem. These are all the critical numbers of this function. You will see if you graph this one function. So let's graph this one function together and let's see what that looks like in decimals. And you will see that all those numbers will show up as critical numbers, will show up as places where the graph goes up and down. I'm going to put, so what I'm going to do, folks, notice here on in decimals, let me make sure that you actually see this page. Yep, you do. Over here, I am going to click on this kind of range symbol here on the right. Okay, and I am going to put on the x-axis, I'm going to put multiples of pi. A step of pi, pi, I'm going to typeset, and it's going to be pi there. And if I do that, I'm going to put radius. So there we go. Let's see. Oops, what is my graph? Oh, that's 0 here. All right, so these are all going to be multiples of pi. Hopefully, if they don't, then I'm going to have to set it again. All right, so f of x is equal to, I'm going to say x instead of theta, equals to 2 cosine x. All right, so now because we have a very much, there we go, there's cosine x here nicely. All right, very much zoomed out, so I zoomed in now, minus, and then, plus actually, plus sine squared x. All right, so there we go, there's my function. And look at this, so it's got a critical number, a maximum over here, then we got a minimum over here at pi, and we got a maximum at 2 pi, a minimum at 3 pi, maximum at 4 pi, and so on, and moving in the negative direction, one at negative pi, another one at negative 2 pi, another one at negative 3 pi, another one at negative 4 pi, and there's a bunch of things like that. So So these are all, folks, the ones that we found, the x coordinates. Those are the critical numbers. They are indeed critical numbers, as you can see on this nice graph that's given over here in the problem. And that takes care of our first half of the lesson. So the next half of the lesson, we're going to do something slightly more sophisticated. It's not going to be significantly more sophisticated, but slightly more. What I'm going to do now, folks, I am going to discuss about, so let me change the share to the whiteboard. I am going to discuss about these things, but with a narrower focus. So right now, if you remember, if you allow what we just saw in that problem earlier, if you allow your function to be defined all over the place, then it could have an infinite number of maximum and minimum points, local ones, and it could go on and on and on forever. So we don't want that. So we want to limit, in practice, we can always limit our intervals, our definition intervals, to some smaller intervals. So that really makes a difference, because if you limit yourself to a smaller interval, then there's a possibility. So if the interval is closed in particular, so if you have something like the interval, let's say the interval from -1 to 1, and you enclose these points, or let's say this is 2 over here, right, on the real number line. All right, so if you have something like this and your function is defined over here, something, like that, then this function is kind of intuitive, that it's going to have a bunch of points of, local minimum, local maximum, the one earlier, maximum, minimum, and maximum, and another minimum maybe. But these points, the endpoints, will also be important. They will be sort of local something. For instance, this is the local minimum here, and this one here is a local maximum. Could be. They don't have to be, but so basically, you would have, this picture says intuitively, you would have finitely many of those, and then you could choose one to be your highest. And then you would land upon the notion of absolute minimum or maximum. So if you choose the highest of these, so if you have a number of hills in Wisconsin and you measure them, and finitely many, right? You measure them, every single one of them, and you make a table, you can pick the highest. If you have infinitely many, then it's complicated. There may not be the highest one, but in Wisconsin, you can pinpoint this one. Same in the world, right? So if you measure all the mountains in the world, then every single one of them, you can pick the highest, and then that's the Himalaya mountains, right? So what we're looking at here, we're looking at problems where now not only can we find critical numbers, which are potentially local points of minimum and maximum, but also we can find the absolute minimum and maximum by comparing the values at those critical numbers by using tables. All right, so our first example here will be problem 45 of section 3.1. And in problem 45, the question is, f of x is equal to 12 plus 4x minus x squared. And it says here x in the interval 0, 5. And it tells us, the problem tells us, find the absolute maximum and absolute minimum values. So find the absolute maximum and minimum values. All right. So this is something that we can, or we already know how to do, as I said. So all we have to do is to find the critical numbers and then compare the corresponding values and find out which one is the highest, which one is the lowest. So solution. All right, so we find the critical numbers. Let's find the critical numbers. So basically, we calculate f prime, we set it equal to 0, and that's going to be 4 minus 2x. It's very easy to set it equal to 0, and we can see that there's only one critical number, and that is x equals 2. So only one critical number. Is that surprising? No, because look here, folks, 12 plus 4x minus x squared is a parabola. And the parabola has only one vertex, right? So that's the only one. That's x equals 2. We found it quickly. All right, with this number, we're going to make a table. So you might wonder what kind of table, what am I going to compare this one to? Well, we also need to involve the endpoints because those might give you some other types of behavior, so maybe some higher maximum or some lower minimum. So we're going to make a table of values. And in this table, on the first row, I'm going to place the values of x. And on the second row, I'm going to place the values of f of x. So remember, f is the function that I'm looking at, not f prime anymore. So f prime was used to calculate critical numbers, of the slopes of the tangent lines. But f is a function I want to look at. So I want to find the highest values and lowest values for f. So I'm going to start here writing, and it's always helpful, folks. I've seen time and time again, I've taught this class, I've seen people mixing up f and f prime here. So make sure that you write the formula for f, and that way you don't make a mistake. So 12 plus 4x minus x squared. And then you put in this table, you put the number 2, obviously. But also the endpoints of this interval, so there's 0 and 5. It would be nice to put them in increasing order, so let's put them in increasing order. So let's put 0 first. Oops. Let's put 0 first, and then 2, and then 5. And over here, we're going to put the values of f at these numbers. So we're going to plug in 0 here. We're going to get 12. We're going to plug in 2, 12 plus 8 minus 4. So 12 plus 8 is 20 minus 4, 16. There we go. And then we're going to plug in 25. So 12 plus 4 times 20, plug in 5. 12 plus 4 times 5, which is 20, right? And then minus 25, which turns out to be, so let's see, what do we have? 12 plus 10 minus 25 turns out to be 5, I think. Okay, so 12. No, hang on a second. So no, that's not correct. I'm doing that in my head. Sorry, folks. You need a calculator here sometimes. 12 plus 20 is 32 minus 25. That ends up being, folks, 32 minus 25 ends up being 7. All right. So now we have a correct number. So we can see that the highest value is this one. And the lowest value is here. So this is the local maximum. So you can say answer here. Local maximum at x equals 2. Local minimum at x equals 5. That's a fine answer. Or you could say the maximum value, and you can pick the value from the second row of the table, is 16, and minimum value, whichever way you want to answer, it's fine. Minimum value will be 7. So whichever way you want to answer, it's fine. One of these two. This is a good answer. This is a good answer too. On the test, so again, I will not subtract points if you write me one or the other. just make sure you know how to differentiate between the two. And then so that we can actually see what we do here, we can put this on decimals, and let me share decimals with you. And again, I'm going to get rid of this function. We're going to move on. We don't want a step of pi. We want a step of 1. All right. And we are going to write the function f of x equal to 12 plus 4x minus x squared. But now, because we want the function to be defined on a smaller interval, I'm going to say 0 less than or equal, if you remember, folks, yep, less than or equal to x, less than or equal to 5. And then we'll put colon and we'll say x squared minus, what is a function? 12. I'm sorry. So got the wrong function. Copy the function from the next problem, negative 12. No, it's just 12. Okay. What am I saying here? So 12 plus 4x. Okay, minus x squared. All right, so this is my function, folks. Let's see what it looks like. Oh, there we go. That's our beautiful function. And over here at 0, 12, you see the points that we just found. So these are the critical, come on. Now, for whatever reason, this one doesn't want to click here. Well, I'm just gonna plot it there, 5 comma f of 5. There we go. So I plotted that point just so make sure that I always have it there. All right, so I plotted that point. I'm gonna put this one here on the picture and this one here as well. There we go. So we got all the points that we need, and we just saw that there is something at 0, and that the value was 12, and then there's a value at 2 and at 16, and then there's a value here at 5, and then the value is 7. And for whatever reason, doesn't want to show me this point nicely. So you can see that the one at 5, the minimum value is 7. You can pick it up from reading the second component. And the one at 2, the maximum value is 16. So yeah, that corresponds to exactly what we did in the table. Now, on the test, folks, if you have functions like that, of course, you can pick up those values from decimals, but explain what you do. So we explain how you get these values. All right. That being said, let's move back and let's do another problem in the same section, and this is going to be our last problem of the day because it will take us a little bit of time. So I'm going to do question 47, and this is, as I said, the last problem here. Let's add one more page, and that is question 47 of section section 3.1, obviously, and f of x is equal to 2x cubed minus 3x squared minus 12x plus 1. And we want x in the interval -2, 3. All right, so this x over here is the following. So again, you want this function. Let's do it quickly in decimals first of all, and let's see how that looks like, what that looks like in decimals, and then we'll do it here. So let's quickly in decimals. Okay, let's do this problem. So okay, let's erase this point. So f of x is equal to now, and again, we're going to do the exact same thing with those curly braces. -2, 3. So -2 less than equal to x less than or equal to 3. All right. And then we have the formula 2x cubed minus, all right, minus 3x squared, all right, and then minus, what is it, 12x plus 1, oops, 12x plus 1. All right, and here's our beautiful function, folks. Okay, so let's zoom out a little bit. Our beautiful function will have a value here, so that's going to be possibly minimum value. No, it's the extreme value, -3 here. We'll have a value here at -1/8, which is obviously the highest on the graph. We'll have a value here at 2, -19, and another value, another extreme value. So this is a local maximum here at 3, -8, but it's not the absolute maximum. Likewise, this one here at the bottom here was -2, -3, was a local minimum, not the absolute minimum. So the absolute maximum and minimum are written here on the picture. So you could say the answer is x equals -1 is a local, is the absolute minimum point, and x equals -2 is the absolute, I'm sorry, -1 absolute maximum, and -2 is the absolute minimum, and the corresponding value are the highest value. The maximum of f is 8, and the minimum of f is -19. So let's do this. We did this quick work with Desmos. Let's do the exact same thing with calculus. So right now we're going to use calculus. We're going to find the critical numbers. And to do that, we are going to write 6x squared minus 6x minus 12 equals 0. That's the derivative here, right? So f prime is that, right? These derivatives, 1 prime is 0. Set it equal to 0, factor 6 here, or divide by 6 the entire thing to get the equation x squared minus x minus 2 equals 0, or this is x minus 2 times x plus 1 equals 0, which gives us the solution x equals -2, and no, I'm sorry, the other way around. So -1 and 2, these are critical numbers. And as we said in the previous situation, what we want to do here, we want to make a table of values. And in this table of values, I'm going to put the x values here and the f of x values here, which f of x is that formula, 2x cubed minus 3x squared minus 12x plus 1, right? So remember, that's f of x. And then we'll place the value. So what values do I want to calculate this function at? So first of all, the endpoints -2 and 3. I'm going to put this here, and in between I have the critical numbers -1 and 2. All right, so we have these 4 values that we want to calculate. At -2, we saw in the previous calculation, or you can just plug in here 2 times -8 is -16, and there's going to be minus 3 times 4, which is -16 minus 12 is -28. But then it's going to be plus 12 times 2, because it's minus 12 times -2, -28 plus 24, that's going to be -6 plus 1, -5. All right, at -1, again, substitute -1 in the formula, -2, minus 3, -5, plus 12, plus 1, -5 plus 13, which is going to be -5 plus 13 is 8. All right, at 2, we're going to get 16 minus 12, 4 minus 24. 4 minus 24 is negative 20, plus now 1 is negative 19. And finally, at 3, we have a larger value, which I'm gonna assume you would calculate yourself. So I don't have a calculator handy right now. So I'm just gonna look here at what we got in decimals, and it turns out that this answer is gonna be negative 8. So I'm going to put negative 8 here. So assume that I calculated, I plugged in 3 here, but I didn't. So I did, but I did this with decimals quickly, and I got this particular value. So obviously, you can strike out these two, and you pick this up as the maximum, absolute maximum, and this one absolute minimum. There we go. So we got the exact same values. You can compare with what we got earlier in decimals, and you will see that it is the exact same thing. So let's quickly look at that. So we got those values at negative 1 and 2, and you'll see that in decimals we got the same thing. So there we go. This negative 1 and 8 and 2 and negative 19. That's exactly what we got earlier with decimals. All right, folks. So that's the last problem I do today. Now, the next thing that I'm going to do very quickly, because this is not something that's going to be on a test or anything, it's more of a theoretical question that I want to go through very quickly here. So I'm going to do two things. I'm going to talk about some things that are more theoretical for the remaining 10 minutes or so. So one of them is the intermediate value theorem. It's also called IVT in math. So if you hear people talking about the IVT, that's what it is. The intermediate value theorem was discussed earlier in the semester when we did continuity. So it was discussed in section, I think it's, yeah, section 1.8. I'm looking here. I was confused first time around when I told you about. So this would be section 1.8, some leftover from section 1.8. Here's what it says. It's a very simple thing. If you have a continuous function and you have a point on the graph below the x-axis and a point on the graph above the x-axis, this is one of the versions of the intermediate value theorem, and you have a continuous function that connects these points, it says that there's going to be a point where the graph crosses the x-axis. So it says that if you know of a function f and some points a and b such that f of a is less than 0, that's what it means for a point to be below the x-axis, to have a value less than 0, and f of b is greater than 0, then you have a point, you can find a point C between A and B such that f of C, so there would be a C such that f of C is actually equal to 0. So that's what the intermediate value theorem says. It can be formulated in other ways, but this is the one that's most intuitive and everybody can easily understand. Proving this theorem is a bit trickier, so I wouldn't worry about that at the moment. I don't think maybe in an advanced calculus class you would prove this kind of theorem. If you're a math major, you would probably hear of this again, but not in any. So maybe in our program, maybe never, because if you don't take advanced calculus, I don't think that's used anywhere else. That's one of the results. And now in 3.2. we talk about the related mean value theorem that has several versions. The easiest version is called the Theorem of Role. And here's what it says. Here's what this one says. It says that if you have a graph and you have 2 points at the same height, So what do we say when we have 2 points at the same height? We have 2 points A and B such that f of A equals f of B. Then if you connect them and you have a function like that connects them, of course, it could be extended this way and that way. So this is y equals f of x here. If you have a function like that and you look at the top, well, there would be some place where there is either a top and there would be some place where there would be a bottom. It can be a straight line. So if a function is a straight line, then of course the derivative is 0. But the point is here that I can always find something that resembles this situation. And if I do so, then I will find a point. So there is a point, a number, I should say. There is a number C between A and B such that f prime of C is equal to 0. So that's very important. Even if the function is constant, of course, then all the points will have this property. So this is called the Rolls Theorem. It's kind of if you want a particular version of a mean value theorem, which mean value theorem can be stated in a slightly more general situation, but you will see the resemblance between this one and the next version that I'm going to state here. This is the most general version of a mean value theorem. This is the x and the y axis. And right now I'm going to take some points, some random points, and I'm not going to make any sort of assumption on the values at A and B. It could be anything. But what I'm going to do, I'm going to connect these two guys. I'm going to connect them. Now, by the way, our function f is assumed to be nice, so it has derivatives and it's continuous and all that. So I'm not going to go into the specifics. I'm just going to tell you the intuitive idea. And if you have a function that, something like that, what this problem says really, in general, it says that there is going to be a point where the tangent is going to be parallel to the line connecting these two. Now, these 2 points are A comma f of A and B comma f of B. And to say that the tangent at this point is parallel at this point C here between A and B is parallel to the line connecting these two on the graph is the same as saying that f prime of C here, folks. So by the way, this f prime of C, let me actually delete the one above here. You know what? I'm going to delete this stuff here because I don't want to be confused with that stuff. Okay, come on. Go away, go away, go away. There we go. So what I'm going to say the slope of a tangent line at C here, above C, is the same as the slope of this line. That's what it means that they're parallel. So that's the same as f of B minus f of A divided by B minus A, because that's the slope of that secant line. So this is the statement of the mean value theorem, the more general statement. Of course, if f of B is equal to f of A, like it is in this case when they are equal, then the difference is 0 and you get f prime C equals 0, which is the previous version that I wrote above here and I just erased. So this is the mean value theorem. Is that useful? Yes, that is very useful for theoretical purposes. But I'm not going to go any further because our time is up today. So I'm not going to assign questions from this section, folks. If you want to see some applications, do contact me and I'll send you a bunch of problems there to kind of look at them if you're curious about this. Our next goal is to do derivatives and graphing and things like that. So we're going through a bunch of routine sections. We're not learning much. We're just kind of doing applications of the things we learned about derivatives. All right, so this is where my lesson ends. I'm gonna stop the recording.